Okay, this fifth lecture in Chapter 8 focuses on drinking water and how we can purify water to make it potable or so that we can drink it. So we've talked about ionic compounds dissolving in water. Um, this happens in the water that we drink. So we know that when water is in contact with certain ionic compounds, those compounds will dissolve into the water. And whatever is dissolved in water determines its quality. Some of the things that are dissolved in water do not impact health. Some of these that are commonly found in natural water are calcium, magnesium, sodium, bicarbonate, sulfates, and chlorides. And again, when these are dissolved at natural levels, they don't cause any health effects. And they actually give us, provide some taste to the water. If you drink water without any ions in it, it has no taste, whereas water coming out of a tap typically has a little bit of a taste to it because of these ions. There are some compounds that will dissolve in water that can cause harm. And as a result, the EPA, the Environmental Protection Agency, has set limits for certain compounds in drinking water. This table shows some of the limits that are placed on drinking water as a result of the toxicity of some of these compounds. The EPA sets an MCL, which is a maximum contaminant level. Again, the units here are parts per million. So what this is saying is that in order for drinking water to be considered safe, it has to have less than 0.005 parts per million cadmium. The EPA also has MCLGs, which are maximum contaminant level goals. These are sometimes lower than the MCLs, and this is what we're striving to obtain, although sometimes we can't obtain those, so we have to rely on the MCLs. Some contaminants that can be found in drinking water are listed here. The first is trihalomethanes, and this can be a result of something like chloroform dissolving in water, usually as a result of some industrial process that is leaking this chemical into groundwater, and this is a known carcinogen or cancer-causing agent. Another water contaminant that we have to deal with is mercury. This enters water as a result of burning fossil fuels. Pesticides, we add pesticides and nitrates to fields to enhance our crop growth. These can run off into our water systems and cause issues. PCBs and industrial solvents are also examples of contaminants that can get into water and do harm. This map just shows an example of some areas that are potentially contaminated, in this case with nitrate. This is a result of agriculture. So we have a map of California, different wells that have been sampled. Green shows areas that are below those maximum contaminant loads. Yellow are within the range of the maximum contaminant load, so we need to be wary of these areas, but they're still below. And then red are the ones that are above those maximum contaminant loads, so you wouldn't want to drink water collected from the areas where we see red. And this is a result of agriculture. So areas that have more irrigation, meaning more water is being added to fields, more agriculture, are areas where you see nitrate potentially accumulating in groundwater wells. When we're talking about water contaminants, another thing that we will refer to is biomagnification. So a contaminant might have a very low concentration in water, but very high in organisms. This is typically found with nonpolar substances. Remember, like dissolves like, so nonpolar does not readily dissolve in water, which is a polar solvent. And so you have very low water concentrations. But when these compounds get into organisms, they can store in the body's fat because fat is nonpolar. So these contaminants get into the fat and the body doesn't have a way to excrete them. So the concentration increases as you move up the food chain. On the flip side of this, polar toxins, remember water is polar, so these dissolve in water. These will be excreted in blood and urine from the body, so they typically don't accumulate as readily. So we need potable water. We need drinking water. How do we make sure our water is safe? Well, in order to do this, we go through a water purification process. These steps that I'm going to outline here is typically used for surface water. So this is when surface water, water from a reservoir or a river, is drawn in as a drinking water source. The first step that happens is that water passes through some type of screen, and this removes large objects such as fish. If you're pulling surface water, you're going to have fish in there, but also things like sticks or garbage, tires, and stuff. So the screens remove large items. The next step is the addition of some chemicals to remove some of those those finer particles. Typically, what is used is aluminum sulfate and calcium hydroxide. This produces a flock or sticky gel or coagulant. Those are all terms that are used for this addition. What happens when you add that aluminum sulfate and calcium hydroxide? You form aluminum hydroxide and calcium sulfate, which is a gel-like material. This scavenges a lot of those smaller particles in the water. Those are allowed to settle out. Once you've removed those particles, the water passes through some type of filtration unit to remove anything else that is left in the water. And then the last step is disinfection. So these steps remove particles, but cannot remove bacteria. That bacteria can cause issues. So we have to add something to that water as a disinfectant. Typically, that disinfectant is done through chlorination. Chlorination is the addition of different chlorine substances, such as chlorine gas or sodium hypochlorite or calcium hypochlorite. These all generate hypochloric acid, HOCl. This kills the bacteria. This is added to the water at the water purification plant, and it remains in the water when it is pumped through our pipes. There are other ways that we can disinfect water. For example, ozone can be added, or UV light can kill the bacteria. But the issue with those disinfection processes is that once the water leaves the treatment facility, bacteria can be introduced into the water, and there's nothing in that water to eliminate that bacteria. This is why most municipal water plants use chlorination, because that chlorine remains in the water and ensures that bacteria does not develop in the water before it gets to your house. People often complain that they don't like the taste of the chlorine. That residual taste in water is often associated with the chlorine. This schematic shows a a drinking water treatment facility. Again, we're using surface water, in this case, lake water. Lake water is pumped through the screens, removing those large debris, your fish, your tires, and any garbage. The flocculating agent here is added. You form that aluminum hydroxide, those calcium sulfates, form that flocculant material. Those chemicals are mixed into the water in the flocculator using paddles. The water then is pumped into a tank where those particles or the gel-like substance is allowed to settle out. The water then is passed through a filter. This filter usually consists of coal and sand. And then it is pumped. First, it is chlorinated as a disinfectant. Sometimes fluoride is also added to the water at this point. And then it is pumped into a storage facility before it enters your house. There's a lot of debate associated with the use of bottled water versus tap water. There is this misconception that bottled water is cleaner than tap water. Actually, there are more stringent laws and requirements associated with tap water than there is for bottled water. So by no means is bottled water a cleaner water source. One thing that is different between bottled and tap water is the chlorination. Oftentimes, bottled water will be disinfected using ozone and UV radiation, not the chlorination process. This is great at disinfecting water, and with bottled water, after it is disinfected, it is put in a sealed bottle so you can't introduce bacteria. As we said, when you are drinking tap water, that water is passing through pipes, so you have to have that chlorine in there to remove any bacteria. So that one difference is that bottled water often doesn't have that taste that is associated with the chlorination, but it is not cleaner, and there are actually less requirements on bottled water compared to tap water. Something else that is commonly done with water is it goes through a filtration process. Oftentimes people will have an activated carbon filter, a Brita filter that they pass their water through, or a filter that is placed on their tap. This can remove residual chlorine to get rid of that chlorination taste. You can also have ion exchange resins, which gets rid of hard water if you have a lot of calcium or magnesium in your water, which can cause soap scum. The hard water is typically removed through a resin. This resin does have to get replaced over time because it does become saturated. So when we started talking about water, we mentioned that a majority of water on Earth, 97%, is salt water. Salt water cannot be used for drinking unless that salt is removed. We do have some means to remove salt from water. Unfortunately, they're very expensive and energy consuming. Desalination plants is one way that we can remove salt from water. We don't see these extensively throughout the world because they are very expensive. One area of the world that you do see a lot of this is the United Arab Emirates, because there's a lot of energy associated with oil there, there's money, and there's the fuel source to do this desalination. One way in which we can remove the salt from water to produce fresh water is through distillation. Distillation works by boiling water. When you boil the water, it goes from a liquid to a gas. That gas then is passed through a condenser, which converts it back to liquid, and you can collect that water. In this process, the salt is not distilled over, so the salt remains in your distillation flask, and you produce pure water. This is hard to do on a large-scale process. You do see distillation occurring often in laboratories to get clean water to do lab experiments. Osmosis and reverse osmosis is another way that we can, another means for desalination. This uses pressure. High pressure pushes pure water through a membrane. The salts do not pass through the membrane. Again, this is an energy intensive process, but it can produce fresh water from salt water.